Hi everyone, thanks for joining us. And in answer to Owen, no, this is just grown like this. It's not actually a cut or a style. This is what happens in lockdown. So no, Hannah didn't cut it. And thanks to Ben giving me some tips, I've put a prop in this otherwise pretty empty and dull room. So yeah, Ben got in touch and asked about whether we could do something to talk about cinema design, I guess, and starting at the fundamental foundation level. When you start to look into that and you think, okay, we're doing this in about a 45-minute session, how much can you really go into? And actually you end up then really focusing in on something which I think will be more interesting, going into real detail on something rather than skimming over the top. So we shall start the presentation. So first of all, yeah, as Ben said, I'm the sales director at DBM, supported by Matthew and Chris on the sales team and a different Chris on our design and specification team. So we distribute a number of brands in the UK, typically based around cinema and multi-room audio. We're probably best known for the cinema design stuff, but we do a lot of multi-room audio as well. So we have a combination of products, so we can supply the best projection systems, in my humble opinion, from Barco Residential. We use display technologies for the screens, but also for the mounting solutions. So if you've been to our office, you'd have seen the vertical mirror mount. And if you see on social media, you'll see some of the mirror drops, which are available from those guys. And then we also have two audio options. One probably obvious is Meridian Audio, and the other one is Waterfall Audio, who joined us in February last year. And then the room acoustic treatment that we use is the CAT system, the complete acoustic treatment system, which I think you'd have seen more about on Neil's webinar last week. So let's go into a bit more detail then. So first and foremost is audio layout. I've kind of put in a section just for 2-channel on its own, although we'll be using the same diagrams that we use for surround sound. And then we'll look at surround sound and the more common Dolby Atmos layouts, and also talking about why we have these layouts in the first place. So let's get into it. So if we look at angles in the first place, you'll often see this perfect triangle, and of course we've drawn a perfect room. It's about 6 by 4 meters that we use in this and these examples. The real world differs in almost all circumstances. This course is really based on best practices in a dedicated cinema room, and we'll talk about some of the challenges that you might see in the real world once you start to design and integrate these systems. So typically, if we start with the left and right channels, we typically want to be in between this 22 and 30 degrees from that center line. So overall angle 44 to 60 degree angle, and that's going to give us a nice stereo image. And stereo image means we're getting audio from both channels, left and right channels, and that information is received by our ears and then translated by our brains to create this wide soundstage. So stereo imaging, it breaks away from hearing 2 speakers and instead hearing this big soundscape. So you will hear sounds in the center that aren't necessarily from the center channel. You will hear sounds which are broader than the screen as well if you have good stereo imaging in the first place. And so if you are selling a system that is a pair of speakers, for example, then that's the kind of ratio you want to be aiming for. Typically, we're going to be installing speakers in the wall, and even more typically behind a screen. And with those types of installations, you don't generally have a lot of flexibility in the mounting because the wall is the wall. Now, if we are using in-room speakers, for example, then we do have more option of towing the speakers in. So that is steering the audio even more directly into the central position. And that's typically, if you're doing a 2-speaker system, you are looking after one person's ears. In a cinema, system, you'll be 3, 6, 8, 10, 12, 30 people. So when you are putting speakers in the room, you have that ability to steer and get even more focus onto that sweet spot. And the reason that we mention that is that the type of in-room loudspeaker you might use might have a different type of tweeter, a waveguide or otherwise, which has different dispersion characteristics. So you have that flexibility. And again, in fact, actually, it's a whole other subject, is talking about how speakers interact with boundaries and so on. which we'll hopefully get to cover in some future webinars. It's just there's too much to go into in this period of time. The other option is to say, if you've got the ability to move the speakers, then you can angle or focus the tweeters in. What's important when you're looking at loudspeakers is to look at the dispersion characteristics. How are the speakers putting energy into the room? What sort of coverage do they get? Most manufacturers will detail that information. We can take that information and then we can map that into the room as well. So that's our first speakers done, the left and right channels. So we're looking at that 22 to 30 degree angle from the center line. And then we'll add some more channels in. So in surround systems, you'll start with 5 is the more basic or most basic surround system that you might see. So we talked before, we'll have the front, left and right channels will be in that 22 to 30 degree from the center line. The side channels will be 90 to 110. And you can see this is how this maps out. Obviously, the further away you get from the center of the room, the larger this area is going to be. And there's a reason for having these angles in the first place. It wasn't someone putting their finger in the air and having a bit of a guess. What we're trying to achieve when we have our left, center and right channels, and also when we have our surround channels, is we're trying to fill the entire room with a cohesive soundstage that allows that energy to move around the room. So if we think about it, before we talked about having, let's move that out of the way, we talked about having our left and right speakers to create this nice cohesive sound space across the front of the room. What we're doing here on the surround channels is we're using these two channels effectively to create another stereo image between these two areas, so that sound can go from this speaker to here in a smooth pan. So it doesn't just jump from one location to the other. A combination of volume and also delay times and also part of the engineering and the sound mix will allow the sound to bridge that gap effectively. And that's why these angles are important. And I said before, this room is a nice, easy rectangular room. So, of course, we can put the speakers exactly where we want to in the middle of these angles. And in the real world, you might have something that prevents you from doing that. And that's one of those design decisions that you need to make at the time on the basis of what's in the room and what's an acceptable compromise. This is where it should go. What happens if I've got a window here, for example? Maybe I need to move the side speaker further forwards of that line. One of the biggest things, if you think about systems, we'll talk about 5.1 or 7.1, but we'll also talk about, oh, hello, Barry has disappeared, magic. Sorry, I'm not sure. You don't need to see me, do you guys? You can hear what I'm talking about on here. Yes, so if you're looking at trying to pan the audio around the rear of the room and then also pan the audio across the front of the room, and when we talk about 5.1 or 7.1 systems, that's what we're talking about. And then we go into Atmos. What that typically means for most people is that we're putting speakers into the ceiling. But there's a really big gap already that isn't generally filled from the left channel to the left side channel. That's a big old space to leap across. So this is where you'll start to see on bigger systems, you'll start to see width channels, which will help to bridge some of those gaps as well. Again, there are angles for that, and we can go into more detail. But typically, most systems that we see deployed, not in the UK, but worldwide, are usually 5.2 or 7.4 Atmos channel systems. Higher end channel count systems do have a bit more complexity, but again, it's relatively straightforward. There are guidelines to follow as well. So yeah, this is what we're looking like for the sides, and then this is what we're looking like for the rear channels too. And again, what we're trying to do is angle the position or have the speaker so that we're getting audio into that location. Now, if we build in another layer, which starts to look at additional dimensions, but for me, this is an area that isn't really covered in that much detail. So if we look at the overhead channels, so if we're looking in this instance with 4 channels above the listener, so these will be our Atmos channels. So we have an angle which we're aiming for, which is between 35 and 55 degrees. So what we're looking at here is the max and min locations from there. And then typically what we're saying is that the rear channels are going to be 125 to 150 degrees. So you can see what we've got. We've got a channel above, and that's trying to fire audio down to the listener. Same for the rear overhead channel as well, trying to fire that audio down to the listener, just as we had with the LCRs and also the surround channels. And then typically we'll find the surround back channels will be in line with the left and rights, and as will the overheads. Again, you have flexibility in where you can place these. We found in a room we actually designed and installed at our factory in the DBM lounge. There's an air conditioning box thing here, so we can put this. We can put the front left top channel where we wanted to, because there was a box there. We didn't want to lose the air conditioning for obvious reasons. We don't want it to smell like an armpit in that room. And the other reason is that, you know, that's where it's going to be. So we had to make a decision, which was either move it further away from that position in this domain here, which puts it still within the acceptable angle for down to the listener, or we could move it across into this side. What we did was kept it in line with the front channel and just moved it further across into this still acceptable area. Again, you know, this is where you should, in an ideal world, place these loudspeakers. You can see in some cases the angle that's acceptable on paper actually encroaches into the rear wall as well. So this is what happens when you take guidelines and then you put them into real world scenarios. But what happens when we talk about angles? It's normally always from a top-down view. So we're looking at the room, and we're not really taking into account the relative height of the loudspeakers relative to the listeners as well. And I think that's the thing I'd like to cover in a bit more detail today. So the vertical viewing angles that we aim for, so that is our sight lines effectively. We typically aim for around 15 to 20 degrees because almost all of the systems we designed are residential, and they are for residential properties. The THX maximum is actually 35 degrees, which looks all the way up there. So you can see some of the THX guidelines are based in much larger rooms, more commercial type environments. So you have that angle to take into account. You don't want to be leaning back and looking up at the screen, you know, like when you get to the cinema late. And well, remember when we were allowed to go to the cinema? Yeah, when we were allowed to go to the cinema, then you got there late because you're cool. You had to sit right at the front, and then you had a broken neck. You had to lean back the entire time to look at it. So one of the important angles is the is this angle in the first place. It wants to be comfortable. Front channel height is always going to be linked to where the screen is going to be positioned. If we're doing a system like this with a single row, then we want to be around 1150, 1250 height wise. Now that's going to be difficult if you're using freestanding box loudspeakers, unless they happen to be about 1150, 1250 tall, which is actually about what the height of our 5200, 7200 and Dsp 8000 are, because they're based on people sitting in seats and listening to speakers. So you want the acoustic center of the speaker. So that would be typically the tweeter mid-range area is where you'll get the most vocals and dynamics from. That wants to be as close to ear height as possible. That's not going to be possible if you've got multiple rows. So these red dots here show a second row if we were to have one in this location. So obviously then our ear height is going to be somewhere in the middle of the two, pretty much where we've drawn it on this diagram as well. So the midpoint of the tweeter, that acoustic center of the loudspeaker, always wants to be from a front position in line with the listener's heads. And if it's multiple rows, is it 3 rows, then obviously we'll move the whole thing up. You could see if the room was larger, and we had room for 3 rooms, the screen could go up and still be within guidelines of viewing angles as well. So these are all of the things that you need to take into account, along with the side and rear channels. The idea is the audio from this speaker should be able to reach the middle person in the front row and clear the heads of the people in the back row. Likewise, the side speaker wants to hit the middle person's head in the middle of the row as well. So it needs to go above the people on the side of the room's head. That makes sense. So if your surround speakers are too low, The people in the middle won't really get any of that energy because there'll be a person in a way absorbing that energy, and you'll lose the benefit of all the effort that you put in and putting the angles in the right place. So for us, this is really key. You know, you need to be looking at, can the audio from all of the channels reach all of the people in the seats? If not, then you probably want to be looking at raising the loudspeakers up in the first place. So simple, very, very simple, very, very straightforward, but actually relatively often missed off. Dolby does have a recommendation for this, and it's about 1.25 times the height of the front channels. So that means in larger rooms where the front channels are raised up, because we've got 2 or 3 or 4 rows of seats, the surround channels can also be raised up too. And if you think about it, in the commercial theatre, there's not a chance you can touch the side channels in the room. They're always significantly higher up than any of the viewers in a commercial theatre. For that same reason, the surround channels want to make sure that they can hit into the middle of the room. I mean, it would probably be useful to have a look at what that looks like. So we thought we'd draw that as well. So you can see in this application, the audio, you get good coverage in all of the seats. And that's what you want to be looking for. And it's the same thing as well if we go into more detail further down the line on projection systems. You know, sight lines and also projection lines need to be taken into account to make sure we don't have someone's head on the screen or someone looking at the screen with someone else's head in front of them as well. So these are the types of things that you should be looking at when you're designing the room. It's not just top-down view. You need to take into account where speakers are going to be on the sides of the room and at the back of the room as well, to make sure that you've got that ability to deliver the information to where the listeners are. So it's real simple, but it's something which is very easily overlooked at the same time. So next thing, speaker efficiency. We talk about it a fair amount. It's a really useful bit of information. I remember when I first started back in 2000, not having a clue what that dB thing at the bottom of a speaker is. So you go around the back of it, you look at it, there's a label. It'll have a dB on there, and now it'll have at 1 watt 1 meter, or it might have had at 2.83 volts at 1 meter, depending on when the speaker was made. And I never really understood what it meant, and I never really understood the implication of what sensitivity meant. I only knew that when we tried different speakers on different amplifiers, some went louder than others, even though I used the same volume on the volume control. And obviously further down the line, do some research to find out some more information, and you start to understand the relationship between all of these numbers on the back. So what we're going to do is, and I appreciate some of you may know about this efficiency and the efficiency calculations, but I think we're going to go into much geekier detail of that, so that you can actually take into account amplifiers and actually what an amplifier says versus what an amplifier actually delivers as well. So it's worth keep listening to the end of this one, because I think it'll be quite intriguing when we run some real world examples of speaker and power amp combinations. So this figure is absolutely critical for working out, and this is the important bit, the theoretical max SPL of the loudspeaker, and therefore then its maximum 105 dB distance. Matthew Smith, placement of subs is a whole other thing that I can't do in 45 minutes, along with doing all of these bits and pieces. But yes, no problem. We can cover that in another webinar in the future. So the other number that you'll find is that the speaker will have a maximum power handling number as well. So that says how much power can the speaker accept, or how much power can you put into the speaker in the first place. And if you have the efficiency of the loudspeaker without the maximum power handling, you're not really in a good position to know exactly the max SPL, because you could easily put either have not enough power or too much power into the loudspeaker, and then obviously run the speaker into damage. And all of the figures assume that there's no losses through cables as well. So cabling, obviously passive speaker cabling, when you've got 15, 20, 30 meter runs, you do start to get losses through there as well. So that's another thing to take into consideration. And again, there are links that you can use to find out the types of losses that you might see. So that's the background of it. Let's have a look. So we'll look at two different loudspeakers. One has an efficiency of 95 dB at 1 watt at 1 meter and 500 watts maximum power handling. And the other speaker has 85 dB efficiency with 1000 watts maximum power handling. So actually relatively typical measurements. 95 dB isn't out of the ordinary. 85 dB is pretty inefficient, but does exist for sure. So you'll know if you've got a low efficiency loudspeaker when you have to turn the volume up a long way to get any meaningful output from the loudspeaker as well. So here's what happens. If we want to add 10 dB, so basically a doubling of volume, we'll have to use 10 times the power. So every time we want to increase the volume by 10 dB, then we need to do 10 times the power amplifier in the first place. So you can see straight away at these 1 meter distances, to go from 95 dB to 105 dB with a high efficiency loudspeaker actually requires very little amplification. 10 watts is in the wheelhouse of pretty much any half decent amplifier. Whereas if we go to the 85 dB efficiency, we need 10 times the power just to match what 1 measly watt will do on a 95 dB efficiency loudspeaker. So there's a huge difference straight away. And you can see on the low efficiency loudspeakers, it is exactly that. You need lots of power to get any meaningful SPL from the loudspeaker. So typically, low efficiency loudspeaker, you'll find very, very big power amplifiers are required to drive them. And high efficiency loudspeakers will give you more output with less power. However, in theory, we could hit 125 dB with the 95 dB efficiency loudspeaker, but its maximum power handling is half the amount of power that's required to hit 125 dB in the first place. So its maximum SPL lies somewhere between 115 and 125 dB because of its power handling capabilities in the first place. The other limitation is obviously the power amp in that you're using with that product too. There are other differences. Low efficiency loudspeakers tend to be very quiet, as in low noise, low hiss. So every time you have an amplifier putting power into a loudspeaker, you'll have a signal to noise ratio. So generally speaking, low efficiency loudspeakers are very low hiss. So when the room goes quiet, the speaker is very quiet. And higher efficiency loudspeakers are more prone to that, and they'll be because they are more sensitive. So any bits of noise will slightly be amplified or increased with those high efficiency loudspeakers. So you can find if the speaker is high efficiency and if the power amplifier is not particularly great design with a fair amount of noise in its signal as well, that you end up with a level of background hiss in the room as well. So there are other reasons as to why you might use different efficiency loudspeakers, but these are both fairly typical of what we would see. Most speakers between 89 and high 90s, so 89 and 99 dB efficiency, and the power handling is more down to what the drive units are capable of. So yeah, as I said, huge difference in the sound pressure achieved, and when we then delve into the power amplifiers themselves, we'll find that that difference becomes even more apparent because of the variations that we have in a power amplifier. So to talk about this, I thought, well, actually, maybe easier if we look at an AVR versus an AV processor. So an AV receiver is an AV processor with a collection of power amplifiers built into the same box, whereas an AV processor does the processing side of things, but then needs either an amplifier or active loudspeakers to be driven. So I went on the internet, cleared my usual search results, and looked for an AVR, just a regular, you know, what's possible to go out and buy. And I found one. I thought, oh, that's great. It's got 7 times 145 watts. Perfect. Now, of course, that's the headline figure. That's the big figure at the top of the page. And I'm not going to talk about which brand it was because it doesn't really matter. In that sense, this is really more about do your research when you're looking into these options to see what's going to be a suitable match. And here's why. So you scroll quite a bit further down and you look at the small print and you find out actually how much power am I getting, because this isn't my first rodeo. I have seen that your mileage may vary, so I thought I'd have a look So the first thing I noticed is that when they quote 145 watts in the detail, they actually specify it's just one channel and not 7 channels at 145 watts. Then you start to see some more numbers here. And if you're not familiar, you might not know what any of these bits and pieces mean. So I figured it might be useful to explain what these are. So first of all is the impedance. Now, typically power amplifiers are rated at 8 ohms, and they'll typically have a 4 ohm figure, which is there or thereabouts, will be up to a double of the 8 ohm power. Most loudspeakers have a nominal impedance of 8 ohm. So it's unusual for a power amplifier to be rated at 6 ohm. But as I said, if you go from 8 ohms to 4 ohms, a power amp may even double its power. So 6 ohms means you're probably going to get a higher number because you've just lowered your impedance. So if you were in, trying to make your product look good on the internet, you might quote a lower impedance number. The other thing is 1 kilohertz is 1000 hertz. So that means we're just playing a test tone of 1000 hertz. We're not actually playing a content or otherwise with there. So that should raise some alarm bells straight away, unless you just listen to 1 kilohertz bursts all of the time. The next thing is 1%, and that refers to the distortion figure. 1% is a lot. So typically in premium amplifiers, distortion will be quoted at 0.001 or 0.1. So 1% actually is a large amount of distortion. And then the final part is one channel driven. Great guesses, guys. But I'm not saying any more than that. But let's look in more detail. So, okay, cool. They rated it. They have measured it with 2 channels driven. Wicked. But it's 120 watts. It's not 145 watts. Okay, so we've lost 25 watts. But what's 25 watts between friends? We'll be fine. What did they do? They did 6 ohms again. Okay, cool. And then they did 1 kilohertz again. Okay, cool. Okay, the distortion's 0.3% lower. That's better. And they have measured 2 channels. We can live with 120 watts though, right? Oh, I've lost even more power, down at 80 watts. So what's this then? This is 8 ohms. Oh, that's good. So that's what we would typically see power amps measured at. And then we've measured it over a much bigger frequency range. So this is very typical of the frequency range that we might see, in actual content. You could say that with most of the speakers that you'd use in cinema applications, you'd probably use an 80 hertz crossover. But either way, we've got now a much more acceptable real world scale for our frequency response. We've got a much more really reasonable, although still 10 times worse than you would typically quote. You'd be looking at 0.1% distortion, and we've got 2 channels driven. So what we thought was 7 times 145 watts is actually more like 2 times 80 watts, but there is no number for 7 channels driven. Let that sink in for a second. If we've already lost all of that power by just running 2 speakers, if we're running all 7 channels, or 9 if it's a system that can do Dolby Atmos, we're going to be significantly down on that wattage number. And that becomes important once we start to look into trying to create 105 dB at larger distances as well. So effectively, just as an example, if you were to look at a big beefy power amplifier with a big toroid and a load of capacitors, so effectively these are batteries or reserves for the power amplifier, so when there are dynamic loads, has more current available to it. These are the types of numbers that you'll see from a big proper power amplifier, and partner that with an AV processor. Now, and that is the reason why AV processor and power amps cost more money than AV receivers. That's just the reality. The difference that you get is huge. So for this amplifier, our Meridian 857, we quote 2 times 250 watts into 8 ohms, both channels driven with 0.01% distortion. When we half the impedance, so we go from 8 to 4, we go 500. If you want even more power, you can bridge, so you can combine left and right outputs to give you 1 single channel, and that'll be 1000 watts into 8 ohms, and then 4 ohms, 1.5 kilowatts. Big difference in price for sure between this completely random AVR that I got from the internet, but this is the example that we're looking at, and these numbers are going to be useful numbers, because what you thought you got and then what you are going to get, I think probably all 7 channels driven into 8 ohms, it's probably about 40 watts, if we're being honest. And that is going to cause some real problems with dynamics, with headroom, with clarity, and so on. So that's why AVRs have a place, and that's why AV processors with separate power amplifiers or DSP Active Loudspeakers have a place in systems where performance is going to be more critical. So yeah, always look out for the headline numbers, and this is the same across pretty much all products, to be honest, guys. This is going to be seen on projectors. Check out the anti-lumen numbers, and then check out the actual anti-lumen numbers, and this is something I'd like to cover in a bit more detail. It's not to say there's anything bad about processors, it's just sorry, AV receivers. You just need to look into more detail about where you're using these things. So yeah, as I said, key figures. There's no figure given for all 7 channels driven, but it will be less than 8 watts, because that was just for 2 channels. The reason that's key is because we're listening to multi-channel soundtracks, which will have multiple channels of audio playing at any given period of time. So all of those channels are going to be drawing power from there. So the key things to think about when specifying it is that separate multi-channel power amps will have significantly more headroom in the system. That means they'll have more power available. So when we do exceed the power rating of an amplifier, and our power supplies sag and all the dynamics in our system collapse, we get heavy distortion. When we're expecting a crescendo, we just get we lose that impact. Multi-channel power amplifiers will have more headroom. Now, there is a reason that monoblock amplifiers exist, and that's because multi-channel power amplifiers will ultimately have similar issues, because they still have a single power supply that might be shared for 5 channels or 7 channels or 3 channels. So there will ultimately be a limit on those, and that's why monoblocks exist, because you have a single dirty great big amplifier like the one I showed you a moment ago that's just driving a single loudspeaker. So monoblocks are better than multi-channel power amps. Multi-channel power amps are better than receivers. And perhaps be remiss to not mention that DSP Active Loudspeakers, where each drive unit has its own amplifier, and each drive unit's amplifier is controlled in the digital domain, using DSP, you have even more headroom again. So this is why you start to see the approach that Meridian takes with the loudspeakers when we're specifying and designing these things, because we eliminate any of the external parameters. You don't need to actually measure and check stuff because it's already built into it. So we talked about 105 dB at 1 meter. Now that's great if you're at 1 meter away from the speaker, but probably the screen's going to look pretty big at 1 meter, and you're probably going to be quite far away from the other speakers as well. So what we do is we take this number that we had at 1 meter, and then we look at the useful maths that exist to allow us to work out how that SPL is then driven further into the room. Now, with almost all loudspeakers, if we double the distance, so we go from 1 meter to 2 meters, we'll lose 6 dB of sound pressure level. The reason I say almost all is that you can get line arrays, which is what you'll see out in PA types of applications. When you're into live music venues and so on, you'll typically see line arrays. There are line arrays for the home market as well, and they'll typically see about a 3 dB loss when we double the distance. So that makes sense if you're in a field that it's 50, 60, 100 meters. You need that high SPL, and you don't want to drop that SPL off at longer distances. Reality is, when you actually research into it, it's not just a simple case of saying you get a 3 dB loss with a line array, because at low frequencies, 1.5K and below, maybe even up to 2K, the bass energy and the mid-range energy does typically at lower frequencies track at the same 6 dB loss per doubling of distance. So it's important that whilst it is true that they have a 3 dB loss at double the distance, that's not uniform across the whole frequency range. And for our use in terms of residential types of use, we really like that low frequency part of it. So that's something to take into account. So let's look at our two speakers again. We have 115 dB at 1 meter, which is pretty decent. Like, that's a decent sound pressure level for you know, for a room that's probably 5 meters in distance, something like that. As soon as we go from 1 meter to 2 meter, which is the first double, and it's actually then still not very far, we've lost 6 dB already. And then if we move to 4 meters, which is much more like you know, the type of listening distance that we might see in a smaller UK-based cinema, we lost another 60 dB, so we're down at 103 dB. And then if we go all the way out to 8 meters, we're at 97 dB. So we lose our sound pressure level very quickly. And it takes a lot of SPL and a lot of power to hit 105 dB at long distances. And perhaps one thing just to talk about is, we talk about this 105 dB figure. The important thing is that that's not meaning that we're going to sit and listen to a film at 105 dB for an hour and a half. That is the dynamics of the movie. So the other end of the 105 dB is an 85 dB dialogue normalization. So 85 dB is what we would expect the voices of the actors when talking to measure once the system's been calibrated. So if you're watching a film and there's two people talking, you typically will see an SPL meter hovering around that 85 dB number. Now, if they're whispering, it's lower than that. If they're shouting, just as if they're shouting in real life, we're going to be higher than that. And the reason for 105 dB is we've got 20 decibels of headroom over normal speech. So we can go twice as loud and then twice as loud again over regular dialogue. And the reason we have that is because if we were having a chat and a gun went off, because that's what seems to happen in a lot of films, that gun should be a shock moment. You know, and having that ability to have a dynamic leap from people talking at 85 dB to all the way up to 105 dB in an instant is a more realistic way of, one, recreating what's happening, and two, a more realistic demand on the system. There are exceptions. You know, we do have big battle scenes, fight scenes, whatever, in movies where you'll have 105 dB peaks and transients for significant periods of time, but certainly you won't be listening to a movie at 105 dB all the way through, because you'll probably have hearing issues at the end of it. You might enjoy it once, but tinnitus and long-term hearing damage is likely to be an issue. So that's why we have 105 dB in the first place. And this you can see straight away with 115 dB loudspeaker. We're somewhere around 3.5, 3.8 meters for our 105 dB peak. But is it though? Is it really though? Remember the two speakers we talked about earlier, where we talked about, yeah, is it the two speakers we talked about earlier, the 95 dB efficiency, 500 watt max power handling, and then our old lazy friend, the 85 dB efficiency, 1000 max power handling loudspeaker. Well, why don't we factor in the distance, because this is a typical room, right? 6 meters by 4 meters, that sort of screen size. And then let's factor in our not 145 watt amplifier as well, because, you know, it isn't, it's 80 watts. Straight away, what we could achieve with that loudspeaker is instantly limited by our power amplifier. It doesn't have enough beans, enough power to make 105 dB at our listening position. And neither did our 85 dB efficiency loudspeakers, got nowhere near that. That's the difference. When you start to look at actually how much power something's got, your ability to drive that room drops off significantly. And realistically, it's probably not even 80 watts, as we said before. And this is where you have to be really careful once you're getting into designing these types of systems, because if one manufacturer is economical with their specs on what they're actually going to be bringing to the table with that power rating, with that light output from their projector, with the max power handling of the loudspeaker, you are going to start to run into issues where you're going to be running into distortion. You're going to potentially be running into issues of damaging drive units. It's typically more damaging to have a low power amplifier overdriving itself into a loudspeaker, because any of its issues when it runs out of power reserves, any of the distortion that it creates can then damage a mid-range drive unit or a tweeter, and you don't want to be taking screens off walls and replacing tweeters because power amp didn't have enough headroom in the first place. You're far more likely to damage a loudspeaker when you don't have enough power to drive it in the first place than you are by putting too much power into it. And no, that isn't a challenge. So let's actually look at this. If we wanted to hit the theoretical max SPL of these loudspeakers, which allowed us to hit 105 dB at 3.8 meters, we would need that original actual real life power that the amplifier quoted. We would need about 145 watts. We would need quite a lot more watts, 1,430 watts to be precise. So then, you know, this is the difference between a big 1.5 watt kilowatt like an 857 versus something like a G55 or a G57, one of the more regular, you know, 5 times 100 watts, which is 5 times 200 watts into 8 ohms, or a 2 times 200 watt type amplifier. So what we're getting at is, realistically, for most quite average loudspeakers, you know, that 95 dB efficiency loudspeaker, if you really want to be hitting the sound pressure levels in real life, in real dynamic load testing, you are going to want to be you know, using those big beefy 5-channel, 7-channel power amplifiers, and you are going to be wanting to use a processor. Or maybe what you do is you use the AVR to drive the side channels, the rear channels, and maybe the overhead channels, and you use a beefy power amp to drive the LCRs because they're the most demanding loudspeakers in the system. So there are steps, you know, there are different ways of apportioning the budget to make this work out. But it's really key that, you know, we are looking at these small details and don't just take something at face value. Do a little bit of research, scroll down the wheel on the mouse a little bit more and find those actual numbers. There are ways of making sure you are hitting those numbers. I am slightly biased because we do sell these products, but I think it's useful just for you to see what is possible without going crazy. So for example, here we use the Waterfall Audio Pro Customs. This is their Pro Theatre range, high SPL, high power handling, high accuracy loudspeakers. Some of you might have heard these, they're hilarious. At ISE last year. Oh, happy days. Remember that, trade shows. And in this case, you know, something like the G57, which is a more affordable but also more regular type power amplifier that you can find. So 1,000 watt bridge or 2 times 200 watts. So this speaker has slightly lower efficiency we've been talking about, but much higher power handling, so 750 watt power handling. So if we run the numbers on that, max theoretical is going to be somewhere between 111 and 121 dB just by using the power calculators, which actually means that with 750 watts, which is within the power handling of the loudspeaker, max 105 dB distance is going to be around 5.5 meters. That is what the type of information that you want to know. So 105 dB at 5.5 meters puts the room at around 7.5 meters, which is pretty much going to be the upper size for most of the UK type projects that we see typically on our design team when we're working with integrators on their projects. The room sizes that we see in the UK probably top out about 10 meters or so, but maybe 6 or 7 meters. The average size is more like 4x6, 4x5, 5x6, that sort of room sizes. So there are products available that don't have to be crazy priced, they don't have to be super esoteric or difficult to get hold of, they don't require power stations to power them, but there are products available that will allow you to hit the numbers that your theory tells you, and also do so without distortion, without breakup, without damaging drive units. And the key bit is here is that it's critical that you're matching the loudspeaker to the power amplifier if you want to get repeatable results in your cinema designs. So this isn't a plug about what we sell. This is more of a detail of saying that this is what's in the marketplace. You do need to be, you do need to be aware, and you do need to be eyes open when you're specifying things, because it's not always as it seems. We also, from the range of the Meridian range of loudspeakers, I mentioned it in passing, of course, but we do have our DSP Active Loudspeakers. So each loudspeaker has multiple power amps, 4, 5, 6, 10 power amplifiers in them, which means that you've got their own power supply. Each one's regulated, each one feeds a drive unit, each one has DSP control. So that is a really engineered solution that means you will hit those numbers. And here's an example of number of power amps that we have in them. But this is the other thing I wanted to highlight, that one, we give a peak SPL meter, which is peak SPL number at 1 meter, which is what you need. Peak is what we're trying to recreate. 105 dB is a peak. It's not a consistent barrage of audio for extended periods. So we do that for the single loudspeakers, and we also do that as a stacked loudspeaker. So these are 125 dB at 1 meter peak is serious. That puts you out at 12 meter 105 dB distance, which is big enough for pretty much every UK installation that I've seen. Another thing that's really worth looking into is the horizontal and vertical dispersion characteristics. These are really key. It's how much spread of audio you've got into the room on the horizontal axis and also the vertical axis as well. So having those numbers helps you to plot where the majority of that energy is going to be in the room. So if you're looking at loudspeakers, it's worth finding out what these horizontal and vertical characteristics are, and also what kind of frequency response you've got. As you can see, I said before, most loudspeakers you run an 80 hertz crossover. Yeah, that's true, you do. With the DSP loudspeaker, with the control that you've got, you can run much lower crossovers. You can get genuine bass from them. And in another webinar where we talk about bass in the room and subwoofer placement, and also crossovers that you might want to use, and we can cover in a bit more detail as to why that's beneficial as well. So hopefully that gives you an insight into where we put loudspeakers and why we put them there in the first place. It gives you an idea about where we want to be positioning loudspeakers and where is acceptable if there are compromises in the room, like I said, an air conditioning vent in the ceiling or a window in the wall or otherwise. What I would recommend is we have our design and specification service. Really nice chap called Chris does a vast majority of these, and he's got tools for you. So if you want CAD files, if you want information, if you want technical specifications and you want to do that yourself, then that's fine. Drop Chris an email. It's design@. And if you wanted to, you're very welcome to send across some drawings and diagrams, and then we can build the cinema from there. And we'll look at all of the things we've talked about today, so SPL numbers and angles, but also projector throw distances, room acoustic treatment, screen size recommendation, aspect ratio suggestions, and why sometimes a 1.78 ratio screen might be a better choice than a 2.37 ratio screen. It's complimentary, so just drop Chris an email and he'll be very happy to come up with a design for you, and that will hopefully help you to win more projects. And typically we'll scale up those systems, and this is where you'll find sort of the biggest benefits to that from your business. You'll have that ability to be confident in pitching to a client why they should spend more money to gain these extra features or this extra performance, and these design packs help you to realize that as well. So we're about 45 minutes, did waffle a bit at the start, so we're pretty much where we need to be. Happily open up to any questions, and yeah, thank you very much for joining us, and yeah, feel free to ask any questions.